So herein we'll talk about NMR spectroscopy. So realize that NMR is one of the most powerful tools that we use here in organic chemistry. The main nuclei that we study is that concerning the proton and the carbon-13. Of course, the natural abundance for the proton is 99.9%, so we get a huge amount of information from that. And of course, carbon-13 is also a paramagnetic nuclei, and so of course we do get a lot of information from it. Realize that we cannot use carbon-12 because carbon-12 is not NMR active. The nucleus itself has to be an odd atomic number or an odd mass number for it to have paramagnetism, so i.e. nuclear spin, or we say that it is NMR active. The nuclei itself has spin, and so therefore it will generate a magnetic field, and therefore we can compare the said nucleus to a spinning bar magnet. Realize that, that spinning bar magnet creates some sort of magnetic moment. Now we're dealing with particles, so of course there are spins plus half and minus a half of these species that are trapped in the nucleus. You can think of the nuclei itself, the paramagnetic nuclei, as a bar magnet, and so if we apply an external magnetic field, then you can see that we can align to give a low energy situation, or align with polar opposite to give a high energy situation, which is less stable. So herein, for example, you can see exactly what's going on. We have a sample, a random sample of nuclei, and as soon as we apply our magnetic field, then of course you can see herein where we have a number of these nuclei are now aligned with the field, and you have a few that are aligned against the field. This creates, from the degeneracy that we had earlier on in the random sample, this creates an energy difference. You got to realize that that energy difference is due to a difference in spin, or reversal spin. So so we've got it here quite elegantly illustrated, where we had a spin which was anti-clockwise, and of course we have the moment pointing in the direction of the field, and here we have it clockwise, and we have the moment pointing against the field. Realize that as we increase the magnetic field, then that perturbation, that increase in energy, difference between the two spins will occur. So herein we're taking advantage of this, because note, right after we apply our field, then of course we have two different spin states. Realize that we can apply radio waves or energy correspond to that frequency gap. This is going to be in the radio frequency, and that will excite our species in the ground state, or in the lower spin state, alpha spin state, to the opposing beta spin state. We say here that we have had a spin flip. A spin flip. A spin flip is really when we have a nuclei in resonance. So we apply a energy in the radio that corresponds to that energy gap. So we're promoting this nuclei to this higher energy beta spin state. yes, and this is the amount of energy absorbed. And we say that we are in resonance with said nuclei. The energy difference, of course, is proportional to the magnetic field. And you can see herein, right, yeah, we can have the direct proportionality of the frequency with the magnetic field. And there's a lot of constants that, of course, are associated with it. This is a diagram that I want you to keep in mind. We'll go back to it later. But realize that each proton in a organic compound does not have the same chemical environment, i.e., yeah, they do not always have the same chemical environment because the electronic environment differs. Yeah? Or I should say they do not have the same electronic environment. You can see that once we have electrons around our nucleus, we now have electron spin creating a small magnetic field which opposes the applied field, and so therefore we have a difference in where the nuclei resonate depending on what environment that nuclei is in. This is a typical spectrum instrument that we use for acquiring the proton. We usually have a sample in deuterated chlorophyll because deuterium is diamagnetic, and so it does not get in the way of you analyzing your protons. We have a tank filled with liquid nitrogen surrounding liquid helium, i.e. cooling liquid helium, which in turn cools superconducting magnets. And then inside this huge instrument, then of course we have a small sample, yet spinning as to create some sort of homogeneous event. So herein you have a sample tube inside the magnet, and what we do in the modern instruments is quite simply we have a strong magnetic field, and then what we do is apply white radio frequency, so a whole range of radio frequency, and then have a detector which detects the absorbance. And so we use Fourier transform to figure out what peaks were being created. And this is the sort of information that you get from your proton spectrum. The number of signals, which is how many different types of protons are present. In this case, we have at least 3 main types of protons, because 1, 2, 3 signals. The location, i.e. we call this a chemical shift, it's in parts per million. It is a frequency scale here on this x-axis, and you can see that in this signal is at 1.2 ppm, while this one is at 2.6, centered around 2.6 ppm, and this signal is centered around 7.2 ppm. The signal ratio, we can't tell at the present moment, but the signal ratio or signal area is called the integration, and it shows the number of protons of that type that we have. So underneath this will be a certain area that will tell us the number of protons we have. And of course the spin, the signal splitting or spin coupling. And you can see here, for example, that we have a multiplet, and here you can see there's like 4 tiny peaks coupled together. So this is a quartet, and here we have three peaks together, and this is a triplet. This shows the number of protons on adjacent atoms, and each of these we'll cover as we move along. Firstly, though, I want to say, how do we interpret these spectra? We have to count the number of signals. We use the chemical shifts tables to correlate those shifts and determine the relative area, and so we can then interpret the splitting pattern to see exactly what species are present adjacent to other species, and then we join them together similar to a jigsaw puzzle. Herein, for example, and I want you to come back to this this spectrum, or this part of the lecture, once we complete our lecture, and review it again to see how much we grasp from it. But you can see here we have a spectrum. On the x-axis, of course, is our ppm scale, and it's a compound of molecular formula C3H7Br. We see three distinct peaks at 3.4, chemical shift 3.4, 1.8, and 1.1 are known. And you will know too that this peak at 3.4 ppm here is most likely due to its proximity to an electronegative bromine. So the hydrogens, that are on a carbon, that responsible for this peak, are close to bromine. We say that it is quite deshielded. We'll get to that later. And of course, so you can see again, if you look closely at your peaks, you'll see that, there's an integration of 3 to 2 to 2, of the 1.1 to the 1.8 to the 3.4 peak. This is telling you that this is the ratio of protons to each other. Now, I know and you know that the ratio is also a type of empirical system, and so you can see it corresponds to the number of protons in the molecular formula. There's 7 protons, and we have a ratio of 3 to 2 to 2, so each of those numbers corresponds to the number of protons that we have in our sample. And if you look at the multiplet, we have a triplet, a sextet, and a triplet. A triplet is telling me that I have 2 protons next door to this set of protons. I have here, this sextet is telling me, sextet 1, 2, 3, 4, 5, 6, 7, sorry, it's 6, it's 6 peaks. It's telling me that we got 5 protons as neighbors, and this one is telling me that I have 2 protons as neighbors. So when I put it all together, I come up with this structure. This is bromopropane. So this one here, we stated that this methyl, which appears as a triplet, is next door, is not next door to this methylene, which is next door to a bromine, which appears as that triplet. The methylene in the center, has 5 neighbors, 5 proton members, and that appears as 5 plus 1 peak, which is a sextet. So let's continue. So you can see here why we have 3 different types of protons at the present moment. It's a crudely resolved spectra for this compound. These protons are said to be, chemically equivalent. These ones, fairly chemically equivalent with the power of the magnet. These two here are chemically equivalent, and these three here are chemically equivalent. That's why they are in those regions, appear as single peaks. If you push on, we can test for equivalence by replacing hydrogen's different protons, and if they give the same compound, then we say they're homotopic. Homotopic have identical chemical environments, and so they'll have identical chemical shifts. So herein we're looking at ethane, and if I change one of those protons to bromine, on these me files, for example, you can see that these result in same compounds. Same compounds, really, because we're rotating around that carbon-carbon bond. So all 6 hydrogens of ethane are said to be homotopic, and therefore the chemical shift is equivalent. In the case of ethane, therefore, we have one signal in its proton NMR. Herein, we're looking at bromoethane. And look closely, because now, if replacing hydrogens and we end up with different compounds, then we say the species is these protons are heterotopic. So herein, I'm replacing one of those hydrogens with chlorine. At the present moment, you can see that those 3 protons on the left-hand side in that me file are homotopic, so they should give you 1 proton signal. However, and we can also replace these 2 guys, and these guys are also homotopic. However, replacing those 2 guys here, you can see that will give you different compounds. And so we say that those are therefore heterotopic. So the me file itself, all the protons are homotopic. The methylene, all those protons are homotopic, but the protons on the me file and the protons on the methylene, they're heterotopic to each other, i.e. they appear as 2 different signals. Look at this fella here. You can see here, for example, we have these alkenes, and you can see that all those me files on top are homotopic, and so they appear as 1 signal because there's a center of symmetry here and here. On the other hand, we see no such line of symmetry, no center of symmetry, but we don't see any line of symmetry here or here. And so and we cannot rotate around this bond, and so these protons are going to appear as 4 different signals. So herein we got this fella here, it's a quartet, and then of course we have some singlets here, and this appears as a doublet. This one appears as a doublet here. So the methyl bromide, as we stated to you before, you can see will give you 2 sets of protons. Herein, we're looking at this alkene, and you can see that we also have a line of symmetry here, but there is no line of symmetry here, and so these guys are, there's 2 different sets of protons. Herein, you can see there's a line of symmetry here, and so we have those 2 being equivalent or homotopic. Those 2 sets are homotopic, and that is quite different from that one. And so we end up with 4 signals. What about this one? be very careful, because you can see herein there is a line of symmetry here. Yeah, symmetry here. You could just call it here. There's some sort of reflection across here. Yeah, and so therefore you see those are equivalent. Those two groups are equivalent, and there is a set of equivalent protons there as well. And so we have three signals. If we replace a hydrogen and we yield enantiomers, then of course enantiotopic hydrogens will have the same chemical shift. So herein, for example, we have the bromo ethane that we covered earlier, and you can see if we replace either one of those hydrogens, there's a mirror image here, and so therefore you can think of that as sort of a mirror image between them. They're enantiomer, and therefore these guys would appear as the one signal as we saw earlier. Herein you can see we have a chiral center here. Why? This is not chiral, but if we do use our imagination and replace it with a group, then of course now we have a chiral center here, and you can see immediately that realizes a diastereotopic system. Diastereotopic systems, yet on the rare occasion when we have molecular rigidity, they can show a difference in their signals. Yeah, so it all depends on the power of the magnet and the restrictions that occur in the molecule. Perform the replacement test on the protons shown in the molecule below, and answer how would you describe the relationship between these protons. Let's have a look at that, and we'll talk about it in class. So now we're going to talk about the chemical shift. I want you to remind you of the diagram, this diagram that we saw earlier, where the proton surrounded by the electron density, will have these electrons spinning around it, and literally they create a magnetic field that opposes the applied field. And of course this lowers the frequency of your NMR signal. I would state that we say that this lowering is shielding. It's a shielding effect, or the shielding lowers your NMR signal. Here's a better diagram. So if you look here, right, we have here our applied field. Yes, this is our applied field B0. And on application, then of course it induces a magnetic field from your spinning electrons. This will oppose, as you can see, it opposes your applied field. And so your effective field is less than your applied field. And so therefore, because it is less, then of course it will resonate at a lower frequency. We say that it is shielded. So the more electrons you have around your nuclei, then the more shielded your nuclei is. So for example, if you note here, so herein you see a summary of exactly what happens in shielding. Increased shielding, is denoted from left to right in our spectra. So we're saying that we're going upfield compared to downfield, where we have increased deshielding. Note that the increased magnetic field that we need for the resonance is when we have a fixed frequency. But reversely, we can think of an increased frequency at a fixed magnetic field. And realize that in today's modern instruments, we use white light, so therefore we're using a range of frequencies, or white radio, so we use a range of frequencies at a fixed magnetic field. So herein is a typical spectrum, and we have here the frequency equivalent of the ppm scale. Now, again, realize that the ppm, right, is the same whatever power magnet you use. And if we're operating at 300 megahertz, for example, 1 ppm will be 300 hertz. The chemical shift itself is the observed shift from your trimethylsilane divided by the frequency in megahertz. The trimethylsilane, by the way, being your standard at 0. The reason why, of course, we use larger fields is that the larger the field, then of course, the better the resolution. So at the present moment, we're looking at low resolution at 250 megahertz, but on an increased magnet, then of course you can see that we increase our resolution. So let's talk about deshielding and anisotropy. These are three major factors accounting for the resonance position of most protons. The deshielding by electronegative elements, anisotropic fields due to pi-bonded electrons in a molecule, and deshielding due to hydrogen bonding. Remind yourself it requires a shorter wavelength of radio waves to cause a nuclei to resonate if it has less electron density around it. So of course, herein we're looking at a hydrogen that's sitting on a carbon, which also has a chlorine. So of course, that is quite electronegative, this element, and so therefore it will have, yes, a deshielding effect on that proton, i.e. it will start to suck away those electrons away from that proton. And so what we would end up having, therefore, is the signal of this proton will appear further downfield. You can see this is an inductive effect, of course. It reinforces this inductive effect, and it's accumulative. So if you look at this chloroform at 3.1, this chloromethane at 3.1, and we compare it with chloroform at 7.3 because of the three protons, the three chlorines. Herein, you can see that as we move away from the chlorine in this chloropropane, then the shielding effect, the deshielding effect decreases. So herein, this methylene is at 3.3 ppm, and this methylene here, yeah, that's on the beta carbon, is at 1.6. We compared, so for example, fluoromethane to bromomethane, and you can see that the fluorine, being more electronegative, causes a generous amount of deshielding. We also see the difference between the methyl, methylene, and methane protons. Methane protons, of course, appear at around 1.7 ppm. Why don't you go ahead and try to predict this fella, and we'll talk about that one during our discussion in class. So herein, we'll talk about anisotropy, or diamagnetic anisotropy. And this is signal location due to pi electrons. So for aromatics, the rotating pi electrons create this cone above and below the ring. Anything within that cone, those cones, are in a shielded region. Anything outside it are quite deshielded. Fortunately for us, most aromatic protons that we're dealing with are deshielded. They're outside those cones. Yes, they're in this region, this deshielding cone. For alkenes, you can see the same event happens. All right, and so for alkenes, you can see that we have those protons appearing at 4.5 to 7 ppm. For aromatics, of course, these appear at approximately 7 through 8 ppm. Herein, the aldehydes are quite unique because not only do we have a severe dipole because of the carbon-oxygen bond, yes, oxygen being highly electronegative, this creates quite a decent amount of deshielding on this proton, but of course we also have the additional anisotropy. And so the aldehydic proton you can't miss. This resonates at 8.5 to 10 ppm. Alkynes is very strange because you can see that the alkyne proton itself falls within the shielding cone, and therefore it's at 2 to 3. This arrow is a bit out of place, but it falls 2 to 3 ppm. So herein, when we look at 14 aniline, we immediately can tell that the protons outside the cone, so in the peripheral, those are the ones that are at 8 ppm, and the ones internally are inside the cone, and so therefore they're at -1 ppm. So with that, we can now summarize signal location. You can see exactly that the TMS is your standard at 0 ppm. Here's our applied field. Of course, we're thinking of a electron. The more electrons you have, the more shielding you have, i.e. the less the effective field, so the lower the frequency. And so herein, look at, say for example, an acid. You can see the acid terribly deshielded. It's a proton, it's naked, and so therefore, it's in that region 10 to 11. So in the shielded region, of course, we can say our proton is highly shielded, upfield, high electron density, of course, and this is in the lower chemical shift region. And of course, it's resonating at low frequency. In contrast, on the left-hand side, yeah, we say we're downfield, etc. So our aliphatics will appear at 1 to 2, and of course, you add some halogens to it, then of course that increase the deshielding effect. And of course, you can see, for example, our alkenes will appear 5, 6 ppm, and the aromatics around 7 ppm, and our aldehydes at 8 or 9 ppm. You can see alcohols, quite strange. The hydrogen bonding, yeah, we can't exactly predict where they're going to turn up, and it depends on concentration. And of course, our alkynes are severely deshielded. Not deshielded, but shielded. Integration, if we look back at the benzyl acetate that we saw earlier, is the number of protons relative to each other. And here we have 3 signals in the benzyl acetate, and it's a 5 to 2 ratio, to 2 to 3 ratio, and that literally tells you, yeah, the relative amount of hydrogens to each other. Multiplicity is terribly important to us, and I think this is the last area we're going to be looking at. And so we'll have a pause and we'll talk about this. So with multiplicity, we're talking about spin-spin splitting, i.e. the n+1 rule. Non-equivalent protons on adjacent carbons have magnetic fields that align or oppose the external field. So therefore, protons adjacent to that, yeah, will absorb slightly downfield when the external field is reinforced, or upfield when the external field is opposed. All of the possibilities exist, so signal is split, resulting in the n+1 rule. So we end up with a varied amount of signal patterns. Let this become familiar to you. So let's have a look. So imagine we have this proton HA, and it's next door to HB. Yeah, HB can align with the external field in some molecules, and in other molecules, HB is aligned against the magnetic field. So it's a 50-50 against and with the magnetic field, and so we end up with a 50-50 peak, i.e. an n+1, 1 proton plus 1 equals to a doublet. Imagine a situation like this. HA is next door to 2 protons of HB. It will be split by its 2 neighbors in an n+1 equals to a triplet. On the other hand, HB will be appearing as a doublet. This is what HA would look like. 2 with the field, 2 degenerate species against and with the field, and 2 against the field. Those probabilities realizes a 1 to 2 to 1 peak, yeah, i.e. a triplet. And of course, you now have HA next door to 3 HB protons, and so we end up with a quartet. There are exceptions to the n+1 rule. So homotopic will not split each other's starters. Yeah. And of course you can see that we have for 1,2-dichloromethane a simple pattern you can predict. You have to have coupling next door to each other, but at the same time you don't absorb germanyl or vicinal splitting. And if there's 3 bonds separating them or 3 carbons separating them, then you do not observe coupling. So herein, if you look at this compound here with molecular formula, yeah, C5H10O, it's a carbonide of some sort, ketone, and you can see there's 2 different signals, and of course, yeah, the methyl appears as a triplet because it has this methylene here, so we get a 2 plus 1. This 2 plus 1 gives you a triplet. This methylene, which is equivalent to this methylene, has 3 protons next door to it. So this corresponds to this methylene, and so it's 3 plus 1. So this methylene appears as a quartet. Now, think about what we did with the bromopropane earlier. And now I want you to go back to the analysis we had at the beginning of the slides and then get back to this. So, you're now back. So, if you note, herein, we have the triplet due to that methyl next door to these CH2s. Then we have this triplet due to this highly deshielded methyl next door to these 2 protons. And then we have this multiplet, which is a sextet, because this methyl has 1, 2, 3, 4, 5 protons adjacent to it. That's a total of 6. And so we see this sextet. Realize that protons next door to each other will couple to each other, and so the distances between those lines will give you what's called a coupling constant. The coupling constant is the same in hertz whatever the power of your magnet is. And with that, we'll now talk about carbon. The carbon is not as strong as the proton because only 1% of the natural carbon is carbon-13. So of course we need sensitive receivers, we need concentrated samples, and we need to have a longer time running this stuff. So splitting is not important to us. Integration is not important to us. The only thing that's important to us with carbon is the number of signals and their chemical shift. So herein, the sensitivity, as I stated before, is pretty poor. And so in this case, I have to use a concentrated sample. Here, for example, again, we see that at the short scan time, the signal again is quite poor. The only thing I see here is the solvent of that the sample is in. But after we scan for 4 hours, then of course we now see quite a number of different peaks present. Of course, you will have different nuclei coupling to each other, yeah, and carbon can couple to protons, yeah, and so when you consider, say, for example, 2-butanol, yeah, here if you had a coupled spectrum, if you have a carbon spectrum, you can see coupling to proton would give you something like this. But as we saw earlier, this becomes very difficult to read, yeah, and so what we do is we decouple, so we tweak it so that we only see the carbon without the coupling with hydrogen. And so we have what's called a decoupled spectrum. Yeah, most carbon spectrums are decoupled. So in this case here, we have 4 carbon signals. Ignore this because this is just our chloroform, residual chloroform solvent. Herein, you can see, for example, I have a comparison between carbon and proton. Here's a proton spectrum running from 0 to 10 ppm, and here's your carbon running from 0 to 100 of 2-bromopropane. And you can see that there's some relative positions, yeah, that you can work with, in the sense that here's the methyls, yes, and some methylenes. Here's a highly deshielded methine, yeah, and here's the methine carbon. Here's that carbon, here's that proton, yeah, in similar situations. So if you look here, for example, we're comparing calculated carbon versus proton, yeah, and it will give you a better idea of how to work with carbons. So as I stated before, the number of signals is terribly important. So for example, we're looking here, number 1, ethane, and you can see that both of these carbons are the same, and so we see 1 signal. On the other hand, we look at this xylene, and of course there's a line of symmetry, a plane of symmetry here, a line of symmetry here, and so therefore those are same, and those you can see are quite different. So what we have now is we have 4 different signals. You can see here there's a plane of symmetry around here, and so therefore you can have those being the same, those are the same, there's a different carbon here, and these guys are also quite different environments, and so we have here 5 signals. Why don't you guess on that one, and then we'll talk about these in class. So, like protons, carbon signals are also affected by shielding and deshielding, and as you can see, the aliphatics, of course, between 0 and 5 ppm, alkynes carbon oxygen between 50 and 100, and of course the aromatics between 120, 130, and these carbonyls, yeah, because of the deshielding due to electronegativity and anisotropy, will appear at 180, 190, and so on. We can also use these to predict our chemical reactions, of course, because that's what we're trying to do, to identify compounds. And you can see here, for example, we got simple elimination reaction, and we're trying to decipher which compound will dominate our spectrum. We can note, yeah, that when we look at the product from this, you can see immediately those two signals here, 120 and 140. You can count the number of signals as well, yes, and you will see that, of course, yeah, that our product is clearly identified as the methyl cyclohexene. Look carefully. Because herein we have two, yeah, important vinyl carbons, but in addition to this, you can see that there's quite a lot more peaks than, for example, the methylene cyclohexene, because you can see here, for example, that this has got 1, 2, 3, 4, 5 signals, while the other species has got a lot more. So in summary, we have the mass spec, we find the degrees of unsaturation, remind yourself of the nitrogen rules, etc. And then with infrared, we can work on functional groups, and with proton NMR, yeah, then we can work on the chemical environment, our integration, our multiplicity, and of course with carbon, then we can find the symmetry of our framework. We'll see you then.